So the molar mass of a gas, there we go, molar mass of a gas. This is actually what we're going to do in lab today. We're going to determine the molar mass of an unknown volatile liquid. This can actually be done quite simply using ordinary glassware. So what we're going to do is we're going to heat a sample of a liquid until it becomes a gas. A volatile gas means that it vaporizes easily. So we're going to heat it until all the sample of liquid vaporizes. Then we're going to measure the temperature, the pressure, and the volume of that gas. And then we're going to let it cool down again. When the gas cools down, it's going to condense and reform the liquid. And then we'll weigh the liquid. The mass of the liquid is going to be the same as the mass of that in the gas state, because changing states doesn't change the mass of something, it only changes the density. So then we'll have the mass by weighing it directly, and the moles we're going to calculate from the gas values of temperature, pressure, and volume using the ideal gas law. And this is the type of experiment that students, you're probably going to be kind of mystified at what the heck are we doing when you're starting out. But once you start doing the calculations and see what you're doing, you're going to go, oh, wow, that is so cool. I mean, it's just elegant. A beaker and an Erlenmeyer flask and a hot plate and some foil, basically. And you're going to figure out the molar mass of this liquid. So let's do an example of this. A sample of a gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. Well, we can use some fancy equation, but I think it's better to just think about it. Molar mass is what? It's the mass divided by the number of moles. So I'm just going to stick that up here. Molar mass equals the mass in grams divided by the number of moles. So it's grams per mole, right? So we need the mass and we need the moles of this sample. Well, here's the mass in milligrams, right? Well, we can convert that to grams. It has to be in grams. 827 milligrams. If we're going to convert, we're going to put grams on top and milligrams on bottom. And so this is 10 to the minus 3, 1, and that ends up being 0.827 grams. That's our mass. The other thing we need is the moles. For liquids and solids, it can be difficult to determine the number of moles that you have. You basically have to do a chemical reaction to figure it out. But with gases, what's nice is you can just measure pressure, temperature, and volume, and you can calculate it with the ideal gas law. So we've got some values in here. We've got 88 degrees Celsius, that's the temperature. Is that a good unit for gas law problems? Celsius? No. We got just kidding. Kelvin. We got to change it to Kelvin. So we're going to add 273.15. 273.15 plus the 88. Well, let's start without other numbers in there. There we go. 361. 361.15. That's the temperature in kelvins. And then they're giving us, I skipped over this one. The volume. Volume is 0.270 liters. And the pressure is 975 millimeters of mercury. So we take the ideal gas law, PV equals nRT, and when we rearrange that,
don't we want to add in ATMs?
We are going to need ATMs, yes. We're going to get N equals PV over RT. So we've got the ideal gas constant in here, and that's going to tell us what units we need to use. R is 0.08206 liter atmospheres per mole Kelvin. And so we've got liters and we've got Kelvin, but this needs to be in atmospheres. So we need to convert that. So the conversion there, and this is something you should have memorized, 1 atmosphere over 760 millimeters of mercury. So 975 divided by 760, 1.2829 atmospheres. So I've got temperature in Kelvin, I've got volume in liters, I've got pressure in atmospheres. So I can plug them into my equation down here. So the pressure, 1.2829 atmospheres. Again, I'm underlining the last significant figure just to keep track, and I'm carrying 2 extra digits to avoid rounding errors. The volume is 0.270 liters. That's divided by 0.08206. Liter atmospheres per mole Kelvin. And then the temperature is 361.15 Kelvin. When you do this on your calculator, be careful. A common mistake I see is that students will do this number times this number. They'll divide by this, and then they'll multiply by the 361. Yeah. I understand why they want to do that, because these numbers are multiplied, but your calculator doesn't understand what you're trying to do, and you have to speak so your calculator understands. If you really want to multiply these two, then you have to put parentheses around both of them. I don't recommend that, but you can do it. I'm going to talk you through what I do. I'm going to do the 1.2829 times 0.270 divided by 0.08206, and then divide by that temperature. Divide by 361.15. So actually get your calculator out and punch this one through and make sure that you're getting the same answer. So I'm getting 0.0116, those are my 3 sig figs, 88, and the unit left is moles. If you got a big number, it's because you multiplied by 361 instead of dividing. And if that isn't making sense to you, I'd be happy to talk to you about it in lab. I just can't take time during lecture to do that. So this is my number of moles. So I've got moles here, and I've got my grams up here, and I just need to put them together to find the molar mass. So the molar mass is going to equal the mass in grams, 0.827 grams, divided by the number of moles, 0.011688 moles. .827 divided by 0.011688. This is my final answer, and so I can round here, and I'm going to get 70.8, and the units are grams per mole. Any questions? Is that a reasonable molar mass? Yeah. How can we even think about that? What's the smallest molar mass that anything could have? One-ish, yeah. If we had hydrogen atoms, the smallest atom, it would have a molar mass of 1.008 grams per mole. Hydrogen atoms, though, aren't found alone. They're found as diatomic molecules, and so it'd be 2.016 grams per mole. That's the smallest molar mass that anything can have. So it needs to be larger than that, okay? Any questions? So, always a good idea to look at your answer and ask yourself, is it a reasonable answer? Sometimes you can't tell, but sometimes you can. And so if you look at it and you're ending up with -5, well, something went wrong, right? Or if you're coming up with 2 times 10 to the -4, right? It's just not possible. Let's do another example. This one's more like a lab experiment. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and re-weighs it. She obtains the following data, and it's all listed out there for you. Calculate the molar mass of the liquid.
That's what we're doing here.
This is what we're doing today. It's going to be very similar to this. Well, what do we need for molar mass? We need mass in grams of the sample, right? And we need the number of moles. So I'm going to write that up here. The molar mass, we're looking for grams divided by moles. Well, it's not giving us either of those directly. Can we figure out the mass of the gas in grams? Yeah, here we have the mass of the flask with the gas in it and the mass of just the flask. So the difference between those must be the mass of the gas. So if I take this one and subtract 77.834 grams, 78.416 minus 77.834, 0.582 grams. That's the mass of the gas. So I'm going to put that in up here. How can we find out how many moles of gas there are? Ideal gas law. So we rearranged that on the previous slide. We came up with N equals PV over RT. The units on R dictate what units we have to put PV and T into. So this is in milliliters. The volume is in milliliters. We need to convert that to liters. Okay, hopefully by now that is something you can do fairly proficiently. The conversion between milliliters and liters involves moving the decimal point 3 places. What happens is students sometimes do it backwards. So think about it for a minute. Can you visualize how big a milliliter is? Think of that 10 mil graduated cylinder, and about 1 milliliter is about that big, right? How big is 1 liter? It's half of a 2-liter soda bottle, right? That's larger. So if I have 213 of those little milliliters, is it going to be 0.2 liters or 200,000 liters? 0.2, okay? So you can do the calculation as I taught you with the milli and the liters and the 10 to the minus 3. Or you can think about it. And so this is going to be 0.213 liters. We do a lot of liter to milliliter conversions. This temperature, that needs to be in kelvins. What's it going to be in kelvins? 373.15 kelvins. Now, because this temperature had 1 decimal place, then the Kelvin temperature is going to have 1 decimal place for in significant figures. And this pressure is torr. I need to convert that to atmospheres. So 1 atmosphere is equal to 760 torr. Torr and millimeters of mercury, exactly the same thing, different names. So 754 divided by 760. 0.992 because there were 3 significant figures in the pressure, and then I'm going to add 2 digits on there, 11 atmospheres. So now I've got pressure, volume, and temperature in the correct units. I'm just going to stick them into my equation down here. So pressure, 0.99211 atmospheres. Always, always write your units. Volume, 0.213 liters. R, 0.08206 liter atmospheres per mole Kelvin. Temperature in kelvins, 373.15. Check the units. Atmospheres cancel, liters cancel, kelvins cancel. I end up with a unit of 1 over moles, which is the same as moles. 0.99211 times 0.213 divided by 0.08206 divided by 373.15 equals 0.0069. 0. There's my 3 significant figures. 1, 2 moles. Is that a reasonable number of moles? Yeah, it is. So if you think of, well, this is 100 degrees Celsius, so that's higher than STP. And the pressure's a little lower than STP, but you know, it's not crazy. 1 mole of gas would occupy what volume?
22.4 liters.
22.4 liters. Well, this is 0.2 liters. So I would expect that the number of moles is going to be less than 1. So if you ended up with, 4,000, yeah, something's wrong. So this is the moles. That goes up here. We take the mass, we divide by the moles. 0.0069012 moles. 0.582 divided by that. And I'm getting with 3 sig figs 84.3. Is that reasonable? Yeah, it is. It's larger than 2. One of the pre-lab study questions was asking you to give a range for reasonable molar masses for volatile liquids. And that's a frustrating problem because there's no one correct answer necessarily. But it's designed to make you think, right? And so we should recognize that the lower end has to be 2, right? So 2, and then how big can a molar mass get? Molar masses can get very large because there are some very large molecules, mostly proteins, things like DNA, that have thousands or even millions of atoms in them. And so those molar masses can get pretty large. But in terms of a volatile liquid, things that are going to evaporate easily are going to have relatively low molar masses. Yes?
We said the molar mass can be infinity then? We just keep that in our
No, there's nothing that has an infinite molar mass. It might have a molar mass of like, I don't know, a couple thousand or something. But it's not going to be infinite. Okay, so there's our molar mass.
How would you answer that question with volatile liquids?
Well, yeah, how would you answer that question? One way would be to think of, well, what volatile liquids can I think of? Alcohol? Anybody think of something else? What about removing your fingernail polish? Acetone? How about gasoline? Is gasoline volatile? Oh, yeah. Well, you could look those up You could just Google them, and it'll give you molar masses, and then say, oh, well, it must be somewhere in there, like, you know, maybe 2 to 100, or I don't know. I would accept the range. I'd accept lots of things as correct for that.